Okay, so on Wednesday we were going through entropy rather quickly in order to really get you started in on the lab so that you could start thinking about that while I was still there. And because of that, we did end up skipping examples 2 and 3 here. So in case you'd like a little extra practice, I thought I'd go ahead and go over the answers. In example 2, if you're going to rank the following in order of increasing entropy, that means that we want the least chaotic to be listed first, and we want to end with the most chaotic. Because of that, you might be able to already see that there are definitely some phases going on here. We've got gas to gas, solid, and liquid. The least chaotic will, of course, be the solid, so C. Solids are very organized. Because they're very organized, they do not have much chaos. Next would become the liquid, letter D. The liquid has a lot more motion, and it's considered a fluid. Since fluids have particles that can change positions, that's going to create more chaos. Solids don't have that kind of mobility. We've now narrowed it down to the most chaotic being either the water vapor or the gaseous hydrogen. Here's where your Lewis dot structures can help you. Water vapor is shaped in sort of a bent structure. Gaseous hydrogen sits in a line. It turns out that the more molecules you have, the more atoms you have, the more possibility the molecule has for various positions. So if you just take, for example, looking at a two-dimensional page, the gaseous hydrogen could maybe go up, maybe you could see it go sideways as another position, each looking at different ways that you could organize the molecule as it's floating through space. The water vapor could be sideways this way, maybe it's sideways this way, maybe it's flipped around. The fact that the water vapor has more atoms attached to it allows it to sit in more positions. That means if water vapor can sit in more positions, it actually has the most chaos. So water vapor is the most chaotic, with gaseous hydrogen not too far behind. All right, example 3. Again, this would be a great way to ask you a very simple question to describe entropy by looking at sort of generic reactions. So let's look at the first one. You're converting from one gas and one solid over to 3 gases. That means we've completely lost the solid and its order, and we've created extra gases, and not just extra gases, but these gases mixed together. That is definitely going to be a positive change in entropy, a nice increase. In number 2, we're going from one liquid over to 4 separate liquids, all mixed together. Again, because of the fact that we're increasing in how many there are, and because we're mixing our products together, that's going to give us a nice positive entropy as we increase the amount of chaos. Question 3 is a little bit harder, and that's because we have a really great gas with lots of chaos and a liquid with some chaos. We then have a solid with not chaos at all, and an aqueous solution. This aqueous solution might very well exist as an ion or multiple ions. It's hard to say. This is the sort of question that I would try to avoid on a test because you're really fighting between a solid with something that is very chaotic, solutions, versus a liquid that has more chaos than a solid, but a gas which is very chaotic. It's that difference between gases and aqueous solutions that makes this one much more challenging. If I had to guess, I'd guess negative in the entropy. But it's also possible that it turns out to be positive, again, based on how big these molecules are going to be.